Okay, so let's do some debugging. So I want to keep sharing, sorry about that, but we don't need peer review anymore. So I'm going to go into, let's see, let's look at step 08. So I'm going to go in and I'm going to mess around here with step 08. It's a relatively complicated. We have a viscoelastic cross. So let's first just in a power law parameter. So here, yesterday someone asked how would we switch from using elastic material to a different type of material, and so we've created when we did the mesh, we had a lower crust and an upper crust. So to switch to a different type of material, we simply go in and say material.lower crust equals that material component. So we've switched from an elastic isotropic 3D component to a power law 3D component. This is a non-linear viscoelastic material. Here we're also using a more complicated spatial database. We're going to get the elastic properties from one database and then the power law parameters for a different database. So here here's where we tell it that we're going to split. Here's where we use this composite database. We say each of those two databases each of them is a simple database. Tell it then for the database A, here's the values that we want you to find in that database. So look for density VS and VP in database A. Here's the name of the spatial database. And then in spatial database B, look for the power law properties. So we have a reference stress, reference strain, and a power law exponent. And these reference values are to non-dimensionalize our physical properties. And look for those parameters in the power law spatial database. So this is particularly useful if you're going to keep your elastic properties the same across a suite of models, but you want to investigate the viscoelastic properties. Say sort of your Maxwell relaxation time, your power law physical properties. You can stick all of those in different spatial databases, and instead of having to regenerate your elastic properties every single time in each of the spatial databases, you can just use a common elastic property database. This is also particularly useful if, say, your elastic properties were, coming from a seismic velocity model or specified in 3D, but your viscoelastic properties were just going to be a 1D depth variation. So in this case, we could have a big database optimized for 3D querying, like on a uniform grid, in one spatial database, but then our very simplistic spatial variation of our viscoelastic properties will be in another database. And so we can optimize and reduce the amount of information we have to provide by separating them into multiple spatial databases. But I'm going to go down here and let's overly constrain our problem. Let's say on the bottom, let's try and constrain degrees of freedom 1, 2, 0, 1, and 2. And see what happens when we try and run this. So you'll see we get an error message, and here's our error message. It says, found overly constrained point while setting up constraints for Dirichlet boundary condition face Z negative, no faults. Number degree of freedom at point 295 is 3, and number of attempted constraints is 5. So it's telling us that we only have 3 degrees of freedom, and we tried to constrain 5 degrees of freedom at that point. And so we would look, the first place we would look would be our Dirichlet boundary condition face Z negative, no faults. But we also could be coming from, that clearly either that Dirichlet boundary condition. We could also try and constrain degree of freedom 0 and 3. And it says we get an error attempting constrained degree of freedom that doesn't exist. Space dimension is 3. And so we tried to, that would tell us if we were running, for example, a 2D problem and we were trying to constrain the 3 degrees of freedom, then it would tell us wait a second, you can't constrain degree of freedom Z, that's not part of the problem. You're running a 2D problem. So let's delete that. I think last time we did messing up the quadrature scheme. Let's see, we can say we have a typo in our vertex info fields. So we don't know how to type strike message. Requested fields not available for output. It was coming from a fault cohesive kinematic object. The field type was vertex, data type was info. So we were using, this was our vertex info fields property. It tells us what fields were available that we could ask for. And it says the field that I could not find was the strike direction with missing the E. And so I could look in here and I would see that, here's how to spell the strike direction. So if I didn't know if there was an underscore or not underscore, this would tell me, what to look for. It also gives you all the available info fields that I could have used. And let's see, let's say we try and run step 21, but we forget to change the problem type. So here's a different kind of data error. So it was trying to configure our spatial database reader, and it says the file name for the spatial database was not found. Now it doesn't tell me, because there was no file name provided, it can't tell me, here's the file name where the error occurred. But what it does give me is it gives me this backtrace information. And so with this information, I can walk down the hierarchy of components to see what spatial database file was not given. So if I start at the top, here's my Pilot app. Then the next thing I see is a problem. And so this is the generic name on the right-hand side, and then this is the specific problem type. So I'm trying to run a Green's function problem, and I see that it thinks my problem type is time-dependent. So immediately, just looking at the backtrace, I would be able to say, wait, I forgot to change the default problem type from time-dependent to Green's functions. Now let's just say that I was trying to that this wasn't an issue, and I wanted to still figure out which spatial database file name I hadn't specified. So I could continue to walk down the hierarchy. So I walk down interfaces. The particular interface in this case is a fault. Is of type a fault cohesive kinematic. I'm within earthquake sources. The earthquake source is just a single rupture. The particular rupture is named E2 kinematic source. I have a slip function. It is the step slip function. I'm providing the slip in a simple spatial database and of type simple IO ASCII, and so that's the file name that I'm missing. So walking down this hierarchy of components, I can pick out exactly where it's finding the error in my parameter. And it's only, in this case, it was by identifying an inconsistency in that hierarchy compared with what I expected the hierarchy to be, that I realized what my real problem is. And this is this happens a fair amount when you don't change, or you think you've changed the default, but you spell it wrong, or so forth. So this is the key is to recognize, because we have default parameters, because we don't want you to sort of to make it easier in running these simulations, instead of specifying every single component, we have default components for a lot of the cases. The one disadvantage is that sometimes you need to change something that you forgot to change. And so walking down this hierarchy of components and looking to see what components are specified compared to what you think the hierarchy should be can help you track down errors in terms of setting up the components. Now, in some cases, obviously, we do forget to specify the file name of the spatial database. So this will catch those errors as well. So let's also go in and actually misspell. So say instead of a fault, let's just call it, say we thought we named our fault San Andreas. So that was this, let's see what file was I running. I was running, so that's step 08, so I better run the right problem for one thing. And so in this case, again, we get file name for spatial database not found. And let's see, did I get any warnings? So I did not get any warnings about a San Andreas component being unknown. So you can end up, but you'll notice that here it was going down. So I was in false in my spatial database. I had interfaces San Andreas. So let's change that back to false. Let's now go up and let's see, where was my, so instead of, let's say we forget to put in, for Power 3D, let's say we forget to put in the first part. So we just say lower crust is Power 3D. See what information we get. So now we get a very different looking error message than what we've seen from before. So it's saying my lower crust component power law 3D not found. And you notice we get also an additional warning here due to it's a result of that component not being found. So this was, you'll see here, it was thinking that we had elastotropic 3D and we were using non-elastic. When our material, we're trying up here to change the material to something other than elastic isotropic 3D. So that's why we get the below warning because our first setting didn't take effect. And so our component power law 3D not found. So that's saying I have something wrong with my line where I'm specifying the power law 3D. And so it's a matter of you have to give it the full name of the component. So in the appendix within the manual, there's a list of all of the components for the naming of all the components. Generally, they make sense. All of our pilot components start with pilot. Then they're broken up by the directory that they're in. This is Python nomenclature. So all of materials are under materials. All of our friction models are under friction. All of the different fault types are under faults, and so forth. Now about 5 minutes left. Has this generated any questions? We have a question here. So the question is it available to make a user-specified material, for example, a Berger's viscoelastic material? So we have templates. So within the source distribution, there is a templates directory. And within the templates, there is a materials and a friction subdirectories. And those are example templates of how you would add your own fault constitutive model and your own bulk constitutive model. You can use those, and you can, without, generally to add in your own, you need to be building from source because you need to generate the component using the same compiler suite and Python version that we used. And so unless you're running on a machine that has the exact same compiler that we used when we built the binary, you're not going to be able to add the component without building from source. However, you don't need to change any of the main Python code. You can add these models that can be loaded at runtime, and that's what the templates show you how to do. Now, for a Berger's viscoelastic material, we have a generalized Maxwell material in both 2D and 3D that has 3 Maxwell components in parallel, and you can select the parameters for those generalized Maxwell components to be consistent with a Berger's body viscoelastic material. And so in that particular case, you wouldn't have to add in your own material. You can just take what we have and adjust the properties to meet your needs. But we do have templates for bulk constitutive models, fault constitutive models, as well as how to add in your own spatial database. But the simple databases are very flexible. We also have a simple grid database, so that if you have even non-uniformly gridded data, but it is on a model that's specified that way, you can you can use that spatial database, and it gives a much faster querying than using exactly what point we need it to do the spatial interpolation. Another question? So yes, every session is recorded. Remember to start recording this session at the beginning. The only session we've missed was this Schedule A Session 1 that we started recording about halfway through. These are currently available. So for each session, you'll know that you can, on the agenda page, there'll be a link and it'll say a streaming version. So right now we're posting links to streaming versions that essentially plays back everything that you see on the screen and streaming, so you can't really fast forward very easily. And you have this whole sort of 2 hours as one chunk. And next week what we'll do is we'll go through and we'll extract and break things up by sort of topic. So like this Q&A part we'll have separate from the rest of the greens functions. We'll separate the 2D and 3D greens functions. And so you'll see, if you go back to our 2011 tutorial, you'll see that we created QuickTime movies that can be downloaded, and then you can play just the piece that you want. And so we have to actually play them back in real time via the streaming, so it does take a while to get through all of those, and so we'll be doing that next week, and we'll get those posted, and we'll send out an email with all of the when those are available. And that also makes it a lot easier so that you can go through and you can try and replicate, and stop the movie and fast forward, reverse to the pieces that you want to see, and follow along on your computer and do sort of replicate what we did on the screen. We realize that we have to go a little too fast for what you to follow along, and sort of retyping all of the commands. So yes, everything will be archived. The slides are posted for all the different sessions. So there's a slides link that you can get the PDF versions, which are higher resolution than what you're seeing on the screen as well. Any other questions before we wrap up? Okay, so a question about Trellis. So Trellis, I believe that I get my qubit from Sandia because I'm at a government agency. Charles is not yet updated to Trellis. He's still using qubit. But in the past, what we've seen is that on Linux machines, there's both a 32-bit and 64-bit version available. On Macs, we have only seen 32-bit versions available. And it's built for OS X 10.6 and later. It may be 10.5 and later. I don't quite remember, but that version is running on my Mac, and I think the same thing will be true for Trellis, that they are available for Windows, Mac, and Linux. I believe your trial version, you have to select which one you want, and each one would only be available for 30 days. Before that, once you start writing them, you have 30 days until the trial version expires. Any other questions? Okay, I don't see evidence for other questions. So we'll wrap up this session here, and we'll come back in 2 hours and talk about, Matt will talk about solvers. And then tomorrow we'll come back and talk about, in 2 days we'll come back and talk about friction, and cover some other, we'll actually make use of the nonlinear solver extensively with the friction. And then the last session will be dedicated to running in parallel both on your laptop desktop machine or on a cluster, and all the issues related to running parallel on a cluster. One word of note is yesterday, due to audio quality problems for the session, we did friction then, and we'll do solvers next. And so if you really want to know what's coming up in friction, you can actually look at the archived version of that video. Otherwise, you can tune in on Friday morning. Friday morning, that is, for West Coast. The other session, we have only about 4 or 5 people, so Schedule B. So if you can double dip and attend both sessions if you want, or if you want sort of more personal attention, just whatever works for you. You're free to join either the Schedule A or Schedule B. We're covering the same content, almost exactly the same in each of those. Obviously, things vary a little bit depending on what questions we get. But all the questions we're archiving and posting, and so you can see what questions have been asked in the other sessions and go back and get the answers. And so I'll be updating the Q&A log shortly with the answers to questions from this session that we've answered orally.